Hello, welcome to another module in this massive open online course. So, we are looking at examples for convex sets and various properties of matrices. Let us continue our discussion, and what we want to look at in today's module is we want to look at the properties of hyperplanes. So, this is example number let us call this is example number 9. So, consider two hyperplanes given by A bar transpose x bar equals B1 and A bar transpose x bar equals B2. Recall that this is the equation of hyperplane. These are two hyperplanes and in fact these hyperplanes, you can see these are parallel. You will realize that these are two parallel hyperplanes. These are parallel hyperplanes, alright. You can draw a figure to denote this. Okay. So, if you represent this pictorially, you will find these are hyperplane 1 and this is your hyperplane 2, and both have the same normal vector. This A bar, this vector is the normal vector, correct. This vector A bar is the normal to both the hyperplanes. These are the normal This is the normal vector to both hyperplanes, and in fact the distance between both these hyperplanes can now be calculated as follows. If you look at this point of intersection of the normal vector with the hyperplanes, that is, if you call these points as x1 bar and x2 bar, this is from your follows from your simple knowledge of high school level geometry or coordinate geometry, that is, these two hyperplanes are parallel. If you look at the points of intersection of this normal with these two hyperplanes, and if you look at the distance of these 2 points of intersection, the distance between these 2 points of intersection, that is the distance between these two hyperplanes. So, the distance between these two hyperplanes is the distance between these 2 points of intersection of the normal A bar with the hyperplane. So, distance between the hyperplanes is the distance between these points of intersection. Okay. And now what are these points of intersection? Remember, the points of intersection are along the normal. So, we have x. So, we have, let us look at the first hyperplane, that is your A bar transpose x bar equals B1. The point along the normal, if you call that as k times A bar, some constant times A bar, then this implies A bar transpose k times A bar equals B1, which implies k times, now A bar transpose A bar, that is norm of A bar square equals B1. This implies the constant k equals B1 divided by norm of A bar square, and this implies point of intersection of A bar that is a point of intersection x1 bar is, this is your point of intersection x1 bar is k times A bar, which is B1 divided by norm A bar square into, that is k times A bar times A bar. Okay, so this is the point of intersection of the normal vector A bar with the first hyperplane. Similarly, the point of intersection with the second hyperplane that is, if you look at x2 bar, x2 bar is all you have to do is replace b1 by b2, that is b2 divided by norm A bar square into A bar. Okay. And therefore, we have found the 2 points of intersection with these hyperplanes of the normal vector A bar with these hyperplanes, and therefore, the distance between the hyperplanes is the distance between these points of intersection. The distance norm of x1 bar minus x2 bar equals norm of b1 A bar divided by norm A bar square minus b2 A bar divided by norm A bar square, the norm of this, which is equal to norm of b1 minus b2 times A bar divided by norm of A bar square, which is equal to magnitude of b1 minus b2 times norm of A bar divided by norm of A bar square, which is magnitude of b1 minus b2 times norm of A bar divided by norm of A bar square, which is equal to magnitude of b1 minus b2 divided by norm of A bar. So, you have this A bar cancelling with this A bar square in the, and you have norm magnitude of b1 minus b2 divided by norm of A bar. This is the distance between the parallel, this is the distance between the set of your parallel hyperplanes which have the same normal vector A bar. Okay. And this is important because this has a lot of applications, this interesting property. So, if you look at the normal, if you look at these two hyperplanes can be used for classification. So, you can have a set of points on one side, a set of points on the other side, and you can use these two hyperplanes to separate these sets of points. Alright. So, this is a classifier. In fact, this is the basis for what is known as the support vector machine classifier. So, this forms this simple principle of maximizing the distance between the hyperplanes. This forms the basis for the SVM, that is your support vector machine. This forms the basis for the support vector machine, and this basically this maximizing the distance between these hyperplanes basically makes the classifier more effective, thereby effectively separating these two different classes of objects. Alright. So, in such problems we are interested in maximizing the distance between the hyperplanes, which is given by, you can see, magnitude b1 minus b2 divided by norm of A bar, and therefore, if you want to maximize the distance between the hyperplanes, you have to minimize norm of A bar. So, if you minimize to maximize distance, that is if B1 and B2 are fixed, you have to minimize norm of A bar. In fact, this is a very interesting property that pertains to classification. Okay. Now, let us look at another very interesting problem. This is number 10, example number 10. We want to show that a set S is convex if and only if its intersection with every line is convex. What this means is that if a set, all right, consider any set, convex set. Okay. Now, if its intersection with every line is convex, that is you take any line and if you look at its intersection with the line, you can clearly see that the intersection with every line is a line segment, which in itself is a convex set. Okay. So, the intersection with any line is a convex set. On the other hand, if you take for instance a region like this, our non-convex set, and if you take any line, then the intersection with respect to this is these two disjointed line segments, and this is not convex. So, this is an if and only if statement. What it says is something very interesting. If the intersection of a set is convex, then its intersection with every line is convex. Similarly, if the intersection of a set with every line is convex, then the set S is also a convex set, and this is easy to verify. You can see this as follows. Let us start in one direction. If S is convex, and the intersection and the if S is convex, now consider any line, given any line, now S intersection line is convex. If S is convex, the set S intersection the line is convex. This is true because S is convex. Given that S is convex, any line is a convex set, we know that. So, convex intersection convex, this is convex, this is trivial. Okay. So, if S is convex, the set S is convex, then a line, any line is also a convex set. So, S intersection with the line, convex set intersection with another convex set, that is also convex. Now, let us flow it in the other direction. If S intersection with any line is convex, okay. Consider any 2 points x1 bar, x2 bar. This implies S intersection with line through x1, because that is also a line through, consider a line through x1 bar comma x2 bar. This is also a line. This implies the intersection with the line through x1 bar plus x2 bar is convex. This implies that if you look at any convex combination, theta times x1 bar plus 1 minus theta times x2 bar, 0 less than equal to theta less than equal to 1, this must belong to S. The reason is the following: because x1 bar x2 bar belongs to S, x1 bar x2 bar belong to the line through x1 bar x2 bar. Therefore, x1 bar x2 bar belong to the intersection of S with the line, alright. Now if you look at any convex combination, that has to naturally belong to this intersection, because if the convex combination does not belong to the intersection, that means the intersection is not convex. Therefore the convex combination of x1 bar and x, because x1 bar and x2 bar belong to the intersection, the convex combination of x1 bar and x2 bar must also belong to the intersection, correct. x1 bar x2 bar implies their convex combination must also belong to the intersection, otherwise the intersection is not going to be convex. Which in turn implies that the convex combination belongs to S. Because the convex combination belongs to the intersection, which implies that S is a convex set. So if a convex set, if you consider its intersection with any line, is convex, and the other direction, on the other hand, or conversely, if the intersection of a set S with any line is convex, then the set S itself must be a convex set, alright. This is a very interesting property and often very useful in demonstrating the convexity of sets, okay, alright. Let us look at another interesting problem that pertains to probabilities. Problem number 11, that is, let x be a random variable and it can take values a1, a2 up to an, and the probability that x takes the value ai, this is given by the this is equal to pi. So this is the probability x, random variable x takes the value ai. Probability x takes the value ai. Okay. Now naturally, if you look at the set of all these probabilities, so we have probabilities a1, a2, an, corresponding probabilities p1, p2, pn. Now naturally, the sum of the probabilities must be equal to 1. First, this probabilities, each of these probabilities, because they are probabilities, they must be greater than or equal to 0, and further the sum of all these probabilities must be equal to 1. Therefore, we must have summation I equal to 1 to n pi equals 1, which is basically also represented by p1 plus p2 plus pn equals 1, and we must also have each pi greater than or equal to 0, and if we denote this by the vector p bar, p1, p2, pn, then remember you can use the component wise inequality symbol to say this vector p bar, each component, remember this is our component wise inequality. This is the component wise inequality, each component of this vector p bar must be greater than or equal to 0. Now we want to examine some properties of this set that contains of this set of vectors p bar. Let us look at the first one, okay. Let us look at all the probability vectors p bar such that alpha is less than or equal to the expected value of the random variable x less than or equal to beta. Set of all p bar that satisfy this. is this set convex? We want to ask this question. Is the set of all probabilities p bar such that the expected value of the random variable x lies between alpha and beta? Is this set convex? Well, that is easy to figure out. If you look at the expected value of the random variable x, that can be calculated as follows, that is summation I equals 1 to n. The expected value of the random variable is probability that x takes the value ai into ai, which is summation I equals 1 to n pi ai, which is basically a1 times p1 plus a2 times p2 plus an times pn, which you can find as a1 bar, a2 bar, an bar times p1 p2 pn. You can represent this as a bar transpose, this is your p bar. So, expected value of the random variable x now becomes a bar transpose p bar, and therefore, if you look at this problem, alpha is less than or equal to expected value of x less than or equal to beta. This implies alpha is less than or equal to a bar transpose p bar less than or equal to beta. Now, this is the intersection of two hyperplanes. You can readily see that this is the first hyperplane is a bar transpose p bar less than or equal to beta. Second hyperplane is minus a bar, that is a bar transpose p bar greater than or equal to alpha, which can be written as a bar transpose p bar less than or equal to minus a bar transpose p bar less than or equal to minus alpha. So, this is the intersection of two this is in fact the intersection of two half spaces, I am sorry, intersection of two this is the intersection of two half spaces, implies that this is convex. Each is a half space, expected value of x is less than or equal to alpha, that is can be represented as the half space a bar transpose p bar is less than or equal to beta, and expected value of x greater than or equal to alpha is another half space. So, this forms the intersection of two half spaces, and therefore, this is indeed a this set is indeed this is indeed a convex set. Okay. All right. Let us look at another set, probability of x greater than alpha, that is the set of all probability vectors such that the probability of x greater than or equal to alpha is less than or equal to another constant beta, or probability of x greater than alpha is less than or equal to beta. Is this set of all p bar that satisfy this is the resulting set of p bar convex? Well, what is the probability that x is greater than alpha? The probability that x is greater than alpha is simply summation of all probabilities pi such that the corresponding ai's are greater than alpha, and this, since this probability x greater than alpha has to be less than or equal to beta, this is less than or equal to beta. This is probability x greater than alpha. That is, you simply have to sum the probabilities of corresponding to all ai's that are greater than alpha, and you can clearly see this is a linear sum, this is a half space, this is a half space, implies once again this is convex. For example, let us take an example to understand this better. For instance, let us say you have a1, a2, a3, a4 or up to A5, A6. Take a simple example, n equal to 6. Now let us say your alpha is here, lies between A3 and A4. So these are less than alpha, so these are greater than alpha and these are less than alpha. So the probability x is greater than alpha equals the probability x equals either A4 or A5 or A6 equals P4 plus P5 plus P6. So probability x greater than alpha less than beta implies P4 plus P5 plus P6 less than beta. This implies basically 0, 0, 0, 1, 1, 1. This is your A bar transpose times P1, P2 up to P6. This is, I am sorry, less than equal to beta. This is your A bar transpose. This implies you can write this as A bar transpose P bar less than equal to beta, and this is a convex set. Okay. So the set of all probability vectors P bar such that the probability x is greater than alpha, some quantity fixed constant alpha is less than or equal to beta is a convex set. Okay. Now what about the second moment, what about expected value of x square? And this is an interesting aspect. Let us look at the set of all vectors P bar such that expected value of x square is less than or equal to alpha. Now we want to ask the question, is this convex? Well, what is the expected value of x square? This might seem a little confusing because x square is non-linear, okay, but look at the expected value of x square. This is summation I equals 1 to n probability x equals probability x equals ai into ai square, that is the expected value of x square, okay, which is equal to P1 times A1 square, probability x equal to A2 times A2 square plus Pn times An square, okay, which is now you can again write it as a different vector transpose times P bar. So I can write this as A1 square, it's very interesting. I can write this as A1 square A2 square times An square times the vector P bar P1 P2 up to Pn, okay. Now this, if you look at this, this is a different vector, you call this as, well, let us call this as u bar transpose. This is your vector P bar, where what is u bar? U bar is this vector, we are now calling this vector A1 square A2 square so on An square by this vector u bar. So expected value of x square, if you look at that, is u bar transpose P bar, and expected value of x square less than or equal to alpha this implies u bar transpose P bar less than or equal to alpha, and you can see this is once again corresponds to a half space. Implies this is, yes, this is therefore convex, and therefore once again the set of all probability vectors, once again the set of all probability vectors P bar such that expected value of x square is less than or equal to alpha, the set of all such vectors p bar is once again convex. All right. So, these are some interesting applications of the notion of convexity, convex sets, some of the properties of convex sets and so on, which have heavy application or which are going to be used very frequently in our discussion on optimization theory, on our discussion on the practical applications of optimization, be it in the context of wireless communication or signal processing or several other fields. So, these form these principles, these examples that we have so far seen form the basic building blocks of several large problems or several large how do you put it, several large paradigms or frameworks that we are going to explore in the future with respect to optimization and its application in several areas of interest. Thank you very much.